Lesson 6.4 is applications of vector addition. So we have a few different applications to consider just as introduction, and you can see these drawings are just so wonderful. If you are a pilot, you might need to calculate how you're going to best steer around dangerous weather, considering the direction and speed of the wind when making flight plans. If this is you and you want to end up there, but the wind is blowing this way, then you're going to have to aim to the west of your intended destination, and the wind will help you out, and you'll get there safe and sound and hit the runway. Also, another situation where you might use vector addition is the force acting on the heavy weight here. Two chains are being used, so you're adding the strength of those two chains in the direction in which they're hanging. Those sorts of things. We start off with pretty easy situations. We start off with situations where the vectors meet at a right angle. Okay, this is called, these guys are tail to tail, but this situation could also be if they were tail to head. Okay, so anytime vectors meet at a right angle and they're perpendicular to each other, we're going to add them together to create a new vector. Then this is called a rectangular vector component. Rectangular vector components. So in this situation, we're going to do some of these, but in this situation where they're tail to tail, right, we would actually finish by forming the rectangle here, and the resultant would be the addition of those two vectors. The blue here is my resultant. The two brown vectors are rectangular vector components of the blue resultant. Same situation here. Here we have head to tail. So the resultant here simply forms a triangle. And the brown vectors that were added together to create vector R are the rectangular vector components of the resultant. Okay, so that's what we're looking at today. We're going to do a handful of examples and get a bit more notes, but we're really just working in triangles, we're working in rectangles, and we are using our trig skills in order to solve these situations. Example 1, resultants of rectangular components. So we're given some information in A. We have a sailboat destination. It's 8 kilometers east and 6 kilometers north of where we are. We're going to draw the resultant. Then we're going to calculate the magnitude and direction. The direction is going to be given relative to the horizontal. So the situation here, we're going 8 kilometers east. And if I wanted to do a perfect diagram here, I would use my ruler and make sure that my 6 was 3/4 the length of my 8. That looks pretty good. So we're going 8 kilometers east, then 6 kilometers north. That means they meet at a right angle. And here we go. Let's draw our resultant. Well, because these are organized head to tail, I'm starting here, following this line, going up that line. The resultant then just completes this right angle triangle with a hypotenuse. This is the resultant vector. And all I need to do to determine its magnitude, so it's drawn, that's part 1. In order to calculate its magnitude, I'm just going to use Pythagorean theorem, right? We know that the magnitude of resultant R, if I take the square of that, that will be equal to the 6 squared plus 8 squared. 6 squared is 36, 8 squared is 64. Add those up, I get 100. Which tells me, now I'm going to take the square of each of those. The magnitude of resultant R is 10. Now as far as its direction with respect to the horizontal, I'm just going to calculate the angle that the sailboat makes with the direction east. Okay, so where the sailboat is, the resultant, we're going to end up calculating this guy over here. We'll call it theta. So we'll call that angle theta. We have opposite and adjacent. Okay, I'm just using SOHCAHTOA here. SOHCAHTOA, reach back into your trig toolbox here. So I have the tan of theta is equal to 6/8. So the measure of angle theta then is the inverse tan of 6/8. And plug that into my calculator, and we'll get an answer of 36.9 degrees. Now, that is relative to this line here, but because we're in a navigation situation, we don't really offer coordinates that way. Remember, we have two ways of doing it. We can either give it as a bearing, which would move around the cardinal plane in a clockwise rotation, right? If I were going to give the bearing, or I can give it as a quadrant bearing. A quadrant bearing would be something like north number toward the east, something like that, right? Which is what's happening. So what I'm really actually looking for is this angle, and same thing in this situation if I was going to do it with a bearing. Okay, I'm really looking for this angle, and what I already have is actually this angle, if that makes any sense to you. Okay, so the angle 36.9 right here kind of fits in here if I'm looking for a bearing, or it fits in here if I'm looking for a quadrant bearing. So what I need to do in order to find that, because I have complementary angles, is I'm just going to take 90 degrees and subtract what I found for theta. So I'm going to go 90 degrees minus 36.9 degrees. That's going to give us 53.1 degrees. And so as a bearing, the resultant vector here has a displacement of 10 kilometers at a bearing of about 053.1 degrees. So the resultant displacement is 10 kilometers, Pythagorean theorem, at a bearing of about 53.1 degrees, or north 53.1 degrees east. Again, Pythagorean theorem to get the magnitude of the resultant vector, and some basic trig here, just SOHCAHTOA, because we're in a rectangular components triangle, in order to get the angle theta, and then in order to represent it in understandable terms with regard to navigation, then we're just going to convert it into bearing or quadrant bearing. You don't need to do both of these answers. It'll often ask for one or the other. In part B of example 1, we have an example. We have the Bay of Fundy. Velocity of water is given as being 2.5 meters per second northwest, the velocity of it, and 3.5 meters per second southwest. So if I'm thinking about my cardinal, my compass here, I've got northwest 2.5 meters per second northwest, and then southwest is at a 90-degree angle to that, 3.5 meters per second southwest. And so I can see that I have rectangular components, and I can see that I'm actually organized tail to tail this time. So I'm going to first go ahead and complete my parallelogram, which is going to be a rectangle. Looks about like that. And so my resultant is going to be from the tail of these two vectors over there. That's going to be the resultant of the vector addition here between the velocity of water. In order to get the magnitude of that resultant, again, I can label this resultant, and I'm going to get the magnitude of the resultant by using Pythagorean theorem. It's going to be the square root of 2.5 squared plus 3.5 squared. You can type that away in your calculator. You will get a magnitude of approximately 4.3. That would be then 4.3 meters per second. It's the magnitude. Now we need the direction. We need the direction of this, okay? Well, what can we do to find the direction of this? We're going to, again, we're finding it with respect to the horizontal. We're going to use Pythagorean theorem. Now, we've broken up our right angle here, but we actually have a right angle here and a right angle here. And so if we choose either of these triangles to work in, let's choose this guy, we're going to have a right angle triangle. We know the length of this leg is 3.5 meters per second. We know the magnitude of that vector. And actually this dotted line is equivalent to the 2.5 meters per second, okay? Meters per second. So all I need to do then is take I have opposite and adjacent. So I'm going to take the inverse tan. Well, let's do it this way. The tangent of angle theta is equal to 2.5 over 3.5. That's opposite over adjacent, which tells us that angle theta is going to be the inverse tan of 2.5 over 3.5. Check that in your calculator. You will get that theta is approximately 35.5 degrees. Okay, you'll notice that I sneakily changed my diagram to make a little bit more sense. It wasn't super accurate, and I want it to be accurate in order to explain this next step to you. How do we get the direction that R is heading with respect to the horizontal? Well, we don't actually have a horizontal here, but we know that if this is heading northwest and this is heading southwest, then that east-west line, the horizontal, would look something like that, okay? And we do know also that if something is heading directly southwest, that this angle here would be 45 degrees. So the vector that's 3.5 meters per second southwest is at an angle to the horizontal of 45 degrees, okay? Why is that helpful? Well, because we know what angle theta is. Angle theta is 35.5 degrees. So whatever's left in here is going to be the angle that we're looking for with respect to the horizontal, okay? So let's write that out. We'll say that again. Since 3.5 meters per second, this vector is 45 degrees below the horizontal, then our resultant is direction of resultant is 45 degrees minus 35.5 degrees. That's going to be the little sliver that's left over up here. That is 9.5 degrees. Now, relative to the horizontal, again, is not super helpful. So we're going to express this as a coordinate, as a quadrant bearing. And so if I finish off my quadrant here, and we've got north, south, west over here, east over here, then we can see that we're going south, and then we're heading back up to our resultant toward the west, okay, as a quadrant bearing. Well, what is that angle then? It's 90 minus angle X that I've marked here, which is this. So the angle that we're talking about as a quadrant bearing is actually going to be 90 minus 9.5. That equals 80.5 degrees. Therefore, as a quadrant bearing, the direction would be south 80.5 west at 4.3 meters per second. Okay, so again, a bit of extra calculating here, but that's because this angle theta wasn't with respect to the horizontal. So we got it with respect to the horizontal by figuring out that little sliver that's left over, but then we said, well, that's for a navigator, that's not that helpful. We need this as a bearing or a quadrant bearing, and so we did that, okay, with respect to south and west. South 80.5 degrees west. Small section of notes on something called the equilibrant vector. I'm going to start just by drawing two vectors. I'm going to give us the vector F1 and the vector F2. And the equilibrant vector is the vector that balances the two other vectors. Okay, so if we were going to, or combination of vectors. So the equilibrant vector is equal but opposite to these vectors. It has equal but opposite. So it has the same magnitude but opposite direction as the combination of these two vectors. So in order to determine what the equilibrant vector is for F1 and F2, we would first need to calculate a resultant vector. Okay, so the combined force of F1, F2 would be this vector, the resultant vector, resultant. And then the equilibrant vector would be the vector that if we set it up tail to tail, it's equal in magnitude to the resultant, but opposite. Okay, so again, I would probably have to bring out my ruler, and I'd have to make sure that this was the same length as this. I'm going to call this vector E for the sake of our notes. What did we do here? We have equilibrant vector. What does it do? It balances another vector or combination of vectors. It is equal in magnitude, but opposite in direction to the resultant. If the equilibrant vector is added to the existing system of vectors, so F1 plus F2, if we were to add vector E, the result would be the zero vector. That means it balances it out, okay? Same thing if we added E and R together, we'd get the zero vector because they have equal magnitude but opposite direction. Okay, to apply the concept of the equilibrant, we're going to find the resultant and equilibrant. So basically we're going to have two separate forces acting on an object. We're going to find the resultant force of those and then balance it out with the equilibrium. So we have a clown here, the mass. I'm just going to jot down some of the important information. Mass of 80 kilograms. Shot out of a cannon with a horizontal force, so straight across, 200 newtons. I'm just going to start drawing a little diagram here. I'm going to call that horizontal, 200 newtons. The vertical force is the acceleration due to gravity. So we could think about this really straightforward. Whenever you're shooting something out of a cannon or any trajectory, it actually does have two forces working on it, right? It's the force of being shot out of the cannon, or for instance, throwing a ball, it's the force of throwing it. But a force that's always acting on a projectile is the force of gravity, acceleration due to gravity, which is 9.8 meters per second squared. 9.8 meters per second squared. All right, I'm going to write that down because we don't know what that vector looks like yet. 9.8 meters per second squared is the acceleration due to gravity. That's heading right down. And times the mass of the clown. Times the mass of the clown. So we're actually going to take this and go times by 80 kilograms. And we end up with a force of 784 newtons. Okay, so the first step is to find the negative vertical force, and it is 9.8 times 80, 784 newtons downward. All right, so that's the second force working here. Sorry, this is supposed to be 2,000 newtons. And then we have 784 newtons downward. We can see that we have a right angle here, which means our resultant is going to start here and become the hypotenuse of our right angle triangle. We're going to call that vector F to represent the forces acting, the combined force acting on our 80 kilogram clown. And to figure out the magnitude of the resultant first, magnitude, we're using, again, Pythagorean theorem. So we've got the absolute value of the resultant squared is equal to both sides squared. I'm just going to go ahead with our values, 2,000 squared plus 784 squared. Quick math on that. The magnitude of force F is approximately 2,148 newtons. All right, to find the direction, we're using trig. We're going to find it relative to the horizontal. So here's our horizontal. And so we're going to end up finding this angle here. And then we will express it as a bearing. Then we'll use that information to find the equilibrium and its direction. Okay, so we have the magnitude of the force here, and now to get this angle, we're simply going to use trig, angle or direction, with respect to horizontal. We have the tan of theta is opposite over adjacent, 784 over 2,000, which means that theta is equal to the inverse tan of 784 over 2,000, which is approximately 21 degrees. Okay, so this angle here is 21 degrees. That is the resultant. And what we're actually looking for is the equilibrium. So what we need to do is figure out, so remember the equilibrium is going to be equal length, but opposite direction to the resultant. So if I had my ruler out, I could do something a bit more accurate here, but it's about like this, okay? That is going to be our equilibrium vector. And so from the horizontal, we know this is 21 degrees clockwise below the horizontal, and our equilibrium, the direction, we know the magnitude. The magnitude is going to be the same here, 2148. The direction then is going to be counterclockwise from the horizontal. We just need to figure out what this angle is. And that's not super difficult. What we have already created here is then an opposite angle. And so the angle that we're looking for is just 180 minus 21. 180 minus 21. So this is all for the, we called it vector F here, resultant. And now for E, the magnitude is going to be the same as the resultant, 2148 newtons. The direction is going to be 180 degrees minus 21 degrees, which equals 159 degrees, and that is counterclockwise from horizontal. And up here we have 21 degrees. This is clockwise from the horizontal. All right, so our equilibrium has a magnitude of 2148, or approximately 2150 newtons, and a direction of 159 degrees counterclockwise from the horizontal. Again, we use the two original vectors of the forces acting on our projectile, and then we find the resultant, and the equilibrium is that vector which balances it all out. E plus F should be the zero vector. So it's the same magnitude, but opposite direction. All right, another little section of notes before we head into our last two examples. The first word that we need to know is heading. So we've already talked about how there can be multiple forces acting on an object. So for instance, if you are driving a ship and the wind or the current is quite strong, you might need to head this direction while the wind pushes you this direction in order to get from here to here. Okay, does that make sense? So what we have, if we are considering these vectors and we're adding these two forces together, these forces are both acting on you as the captain of the ship. You're going to end up coming from here to here, okay, which is the resultant. It's also the bearing. So when we're talking about, you know, which direction are you heading, this is your bearing. This is the way you're actually going to end up going. And that direction is equal to the direction of the resultant. So that is the direction of resultant. And that occurs because you have another force acting against you, that is the wind or the current or both, or maybe they're both going different directions, and then you'd have to have a combination of more than two vectors. But this right here, this is where you are aiming the ship. This is called your heading. Okay, so you set your ship to go a certain direction, the wind pushes you or the current pushes you a certain direction, and where you end up, the direction that you end up, is your bearing. Okay? I have a similar, well, hopefully pretty much identical diagram down here, because here we're talking about direction. Vectors have magnitude and direction, okay? Magnitude and direction. So here we're going to be talking about velocity. Velocity. And again, this is the velocity of an object relative to the ground. It's the resultant or bearing velocity when the heading velocity or air velocity and the effects of the wind are added. So in this case, if you are a pilot, you are piloting your airplane, you are going to end up going a certain direction. And that is based on your air velocity, or sorry, you're going to end up with a certain velocity, a certain speed, because the air velocity, that's how fast you're going in the air, but then there are things in the air that are going to affect you, they're going to work on you, and this can also be considered with boats. I'm just kind of switching the example, the illustration, but this is wind or current, as it's changing your direction here, as it's changing your velocity in this diagram. So again, the resultant is both of these things working on or against you or for you, whether depending on the direction that they're each heading. And this is called ground velocity. Ground velocity. And that is equal to the velocity or the absolute value of the resultant. And here, should have wrote this in blue if I'm going to be consistent. This is air velocity, also called heading velocity. So because this is your heading, this is the way you're heading, you can set the speed at which you'd like to go there, but if the wind or current is working against you, you're going to get there a bit more slowly. If it's working for you, you might get there a bit more quickly. This is also called then the heading velocity. All right, hopefully that at least makes a little bit of sense. We're talking about the direction that we're going and the velocity at which we're going there, and multiple forces can affect that and act on that. So let's go ahead and do an example. Example 3. I'm going to maybe just fit it over here. Example 3. It's a flight problem. We have an airplane. It's flying at an airspeed. Air speed is what? 500 kilometers per hour. On a heading of 40 degrees. And we have more information. We have a wind. The wind is 150 kilometers per hour, and it is blowing from a bearing of 120 degrees. And we need to determine the ground velocity of the airplane and the direction of flight. Okay, so we have two things here. We have our heading of the plane, 040, and we have the direction of the wind or the current. That's from a bearing of 120 degrees. So there's those two vectors, and we're going to calculate the resultant. Okay, but these vectors also have velocity. This vector, the length of this vector, our air velocity, is going to be 500 kilometers per hour, and our wind or our current is going to have a velocity of 150 kilometers per hour. So let's convert this example into a diagram so we can see what's happening here. North, east, south, west. I'm going to take our airspeed, 500 kilometers with a heading of 40 degrees. So a heading of 40 degrees means I'm going to be coming about like that. In order to do an accurate drawing, I should really be using my ruler. Let's go 1 centimeter per 100 kilometers per hour. So I have a 5 centimeter vector there at 40 degrees. Okay. This is our airspeed, 500 kilometers per hour. And then we also have the wind acting on us. The wind acting on us from a bearing of 120 degrees. So let's look at that. We're going to come around here. This is 90 and 30 more is 120 degrees, and it is 150 kilometers per hour. So that's 1.5 centimeters on my diagram. Put the arrow up here. It's kind of hard to see, but that's the direction it's going. Maybe I'll close that triangle and then we can see it a bit easier, a bit more easily. Okay, now because my vectors are tail to head, I can easily draw the resultant. The resultant is right there, heading this way. Okay. And if you need to draw the triangle again somewhere else to get a little more clear view on it, go ahead and do that. What I really need to do here then is to figure out what this angle is. And it's not difficult. I know that from here to here is 120, and from here to here is 40. So what's in this piece here is going to be 120 minus 40, which gives me an angle of 80 degrees there. Okay. This angle remaining here is the resultant, is the angle that the resultant makes with the wind direction. And we're going to end up solving a bunch of pieces of this triangle in order to determine the bearing of the resultant. Okay, the bearing of the resultant. So it's kind of like this whole grid is going to kind of shift relative to this angle once we get to that point, and then we're going to have a bearing for the resultant. But the first thing I would like to do is just figure out what these angles are. In order to figure out this angle, I really need some more information. What I'm going to do first is find the length of, find the magnitude of our resultant. Okay, find the magnitude of our resultant. And it's not a right angle triangle this time, so I'm going to be using cosine law. Use cosine law to find magnitude of r. All right, that looks like this. We've got the magnitude of r squared is 500 squared plus 150 squared minus 2 times 500 times 150 times the cosine of 80 degrees. Carefully put that into our calculator and square root both sides. We end up with a magnitude of 496.440 as the magnitude of our resultant. Okay, so we have this guy, and we have its opposite angle, which means if we want to find out anything else in our triangle, we can use sine law. So we're going to use sine law to calculate angle theta. Okay, there's angle theta. We're going to use sine law to find theta. So we've got the sine of theta over the magnitude of its opposite side, its vector, 500. And that's equal to the sine of 80 over the magnitude of the resultant, which was 496.44. Be as precise as possible. And multiply both sides by 500. Take the inverse sine of both sides. We end up with theta as approximately 82.7 degrees. All right. At this point, I want to redraw my diagram so that I can have the origin right here at the tail of the resultant. It's going to give me a better opportunity to determine the bearing. Try and draw it as exactly the same as I can. And so we now have the resultant. It's going to be coming up like this. Okay. And our other two vectors, our wind speed is like that. And our airspeed is like that. We found out that this angle is 80 degrees. And we also know that this angle, I'm just going to draw it over here, that's 82.7, 83 degrees. And now in order to talk about this with respect to a bearing, I need this little angle right there. Okay, we'll call that angle alpha. And to find the value of alpha takes a little bit of logical reasoning here. If we look back at our first diagram, this original wind vector is 120 degrees, right? So this would be 180, and it's back 60 degrees. So the only thing we've really done in this diagram is if we've taken it from here and translated it up there, which means that this angle from 0 backwards, so from 360 working backwards, is, so this angle is 60 degrees. Okay, so where it was 60 degrees off of 180, now it's 60 degrees off of 360. Okay, so this angle from here to here, if I could do it maybe in a different color, brown. Okay, this angle right here, that's what I'm talking about. 60 degrees backwards from 360. So that means that from this 83 degrees from the blue vector to the red vector, 60 of it is accounted for here, and the remaining piece of it is alpha, okay? So what are we going to do here? To determine the bearing, of the resultant of r, vector r, translate, so the tail of r is at the origin, then use reasoning to find bearing. And we've already talked about it because this angle here, working backwards, was 60 degrees. That means this angle here, this brown mark, is 60 degrees. So what we're looking at then is 83 minus 60 degrees. This is alpha, is equal to 83 minus 60, which is 27, and it's all approximate. And that gives us our bearing. So our airplane then, therefore, plane is flying at a ground velocity. Ground velocity was the velocity of our resultant. A ground velocity of 496 kilometers per hour on a bearing of, oh, did I do my math wrong here? 83 minus 60 is 23 degrees, on a bearing of about 0.23 degrees. And again, that is the direction the plane needs to fly. Sorry, that's the ground speed. That's where the plane ends up as it flies one direction at 500 kilometers per hour and the wind works at it from a different direction at 150 kilometers, then that's what actually happens to the airplane relative to the ground. All right, in example 4, we have a tension situation. A traffic light at an intersection is hanging from 2 wires. They are equal length and they both make an angle of 10 degrees below the horizontal. The traffic light is 2,500 newtons. And we need to figure out the tension on the wires. So we need to figure out what force each wire is participating in order to balance the situation, in order to hold the traffic light right where it is without allowing it to fall lower or pull it up higher. Okay, so what amount of force are these wires acting on the light itself? And a good way to think about this would be to redraw our diagram, okay, as a vector diagram. So we're going to redraw it as a vector diagram, and we're thinking we have a vector here, t1, and a vector here, t2. And if the traffic light is a downward force, then these two vectors must be acting in an upward direction. And what ends up happening, if I redraw this, I'm just going to think about it as our downward force here. Do it in purple still. Okay, that's a downward force of 2,500 newtons, and I need to balance it out. So the resultant of our two tensioned wires needs to be the same length. Would be the equilibrium, or this would be the equilibrium, whichever one way you think about it. This is going to be the resultant. The red one is going to be the resultant of these two wires. It's kind of like this right here, right? And it is going to have a force of 2,500 newtons heading straight up. Okay, so what I'm going to do is I'm actually going to rearrange our two wire vectors in order to have them create this resultant. Okay, now we already know their relationship to the horizontal. Okay, so, and it's 10 degrees from the horizontal. So what's going to be happening here is we're going to organize our tensioners head to tail because they're both kind of pulling up, right? So if you think about it, it'll make sense after we talk about it maybe, and then you'll have another trick in your tool bag. But basically, we've got T1 coming up like this. Okay, my drawings are not to scale. That's okay. We've got T1 coming up like this. And if we translate T2 so that they are tail to head, then we have T2 coming up like this, and then we can clearly see that red is our resultant. We also know these two little angles inside here with respect to the horizontal are both 10 degrees, okay? So this angle is 10 degrees, and this angle is 10 degrees from the horizontal. All right, well, what can we do now? We already know the magnitude of our red vector, our resultant. It's going to be equal and opposite. It's going to be 2,500 newtons upward. That's going to be the combined magnitude of vectors T1 and T2. And we want to figure out exactly what each of those wires, the force of each of those wires, okay? And they're heading at a strong angle, whereas this guy is pulling straight down, okay? So we're figuring out what is the upward force of, well, we know the upward force is 2,500, but they're going to be pulling actually much stronger than that because they're not pulling directly upward. They're pulling mostly outward, okay? If that makes logical sense. So we're going to use trig to solve this thing. First thing we're going to do is find the angles at the base of this isosceles triangle. Okay, it's an isosceles triangle because we know the two wires are equal in length. And so to figure that out, we just need to take this angle, which is 10 plus 10, 20 degrees. So determine, step one, determine angles at base of isosceles triangle. In order to do that, we're going to take 180 minus 20, and we're going to divide that by 2. That gets you 160 divided by 2, which is 80 degrees. Okay, so each of these angles then at the base is 80 degrees. Could have drawn this diagram a bit bigger. That might have helped us. Now what? Well, now we can use sine law to determine the magnitude of each of these sides, and they're going to be the same, so we just need to find it for one of them. To use sine law to determine magnitude of wires. It's the vector indicating the force of the wire, but that's good enough. So what are we doing here? We've got, let's talk about T1, vector T1, and we're looking for the magnitude of that. T1 is opposite an angle of 80, so that's over the sine of 80 degrees. And then our completed ratio is 20 degrees, sine of 20 degrees down in the bottom. And we have an upward force, our resultant is 2,500 newtons. All right, so we're multiplying both sides by the sine of 80. We get the magnitude of T1 is approximately 7,198 newtons. That's approximately 7,200 newtons. That would be good enough. That means that this wire, the length of it, which represents its magnitude, is 7,200 newtons, and this guy is also 7,200 newtons. Because they're both pulling out so much, the upward force that's balancing out the weight of the traffic light ends up being 2,500 newtons, okay? So because T1 and T2 are the same, the wires each have a tension of about 7,200 newtons at 10 degrees below the horizontal. That just means right here. Here's our horizontal, here's 10 degrees below, horizontal 10 degrees below. All right, so it was all about finding the resultant and then balancing out with an equilibrium. And we should be able to do from page 343, numbers 1 through 19, or 20 even. Thanks for watching.